Let H be the set of all vectors x, y, and R2 such that x squared plus 5 times y squared is less than or equal to 1. So we have an ellipse here. And we want to find two specific examples, two vectors, and a vector and a scalar to demonstrate that this set H is not a subspace of R2. So to help us in finding these specific examples, let's sketch H in R2. So again, we have that H is the set of all vectors that are restricted to this ellipse or within this ellipse. So I'm going to think about the ellipse here, this x squared plus 5y squared is equal to 1. So I'm setting it here equal to 1 for our graph, but we'll keep in mind it does have to be less than or equal to 1, so we'll shade the region inside. But I'm thinking of the equality here because I want to sketch the graph. So I'm going to think about what are the x-intercepts and then what are the y-intercepts. So the x-intercepts here, I have x squared is equal to 1. And if we take the square root of both sides, we end up with x is plus or minus 1. So we have x-intercepts at the ordered pairs, -1, 0, and +1, 0. And y-intercepts, so letting x be 0, we have 5y squared is equal to 1. Dividing both sides by 5, I have y squared divided by 5. So we have y is plus or minus 1 by the square root of 5. So in ordered pair form, that's minus, oh, shame on me, that's 0 minus 1 by the square root of 5, and 0, 1 over the square root of 5. All right, so in identifying these x and y intercepts here, it's going to be easier in the end to end up finding a specific algebraic example to support our conclusions. So let's think about this graphically. There's our y-axis and our x-axis. If you do have graphing paper, I encourage you to use it for accuracy, but we'll try our best here. So we know we have x-intercepts. We'll say right there is 1, and here is, or excuse me, there's -1, here is +1. And then we'll say right about there is 1 by the square root of 5, and here is -1 by the square root of 5 for the y-intercepts. And so we can sketch our ellipse by connecting our intercepts. All right, and we're thinking about the space within this bounding curve. So this is our set H here. So using this, we're going to be able to find algebraic examples to demonstrate how this set, or how this space, is not a subspace of R2. So we know that there's 3 conditions for a subspace. The first being that the 0 vector must be in H, and we can see that that certainly holds true. Here's our 0 vector, and that's all set. The second thing we need to show is that H is closed under addition. So if H is closed under addition, this means that we want to demonstrate that for all vectors u and v in H, that the sum of those two vectors u plus v is also in H. So let's think about this geometrically first to prove to ourselves that this is not closed under addition, and then we'll use our geometric interpretation to find specific examples. So if we say, all right, here's vector u, here's vector v. So we can see both vector u and v definitely live in H, no problem. But when we apply the parallelogram rule, we can see we have vector u plus vector v. We can see that we use a different color here. We can see that this new vector u plus v is certainly not in H. So based off of this geometric interpretation, we want to kind of give a guesstimate for the numerical values of these two vectors. So looking at u to get us started here, we want to find coordinates for it. So the x-coordinate we could say is right about 1/4. And then the y-coordinate, because we kind of have a nasty y-intercept, let's use that 1 by the square root of 5 to help us in defining the y value. So for simplicity, I'll say that's 1 by 2 times the square root of 5. So I'll let vector u be the xy, or be the vector with components xy such that x is 1/4 and that y is 1 by 2 times the square root of 5. And we do the same thing here for v. So looking or defining those coordinates of v, we can say that's roughly 3/4. And then if we march over here to the y-axis, again, thinking about that y-intercept, I'll say that's 1 by 3 times the square root of 5. So I have the xy coordinates of vector v is 3/4, and then that's 1 divided by 3 times the square root of 5. So both of these vectors, again, we've confirmed they live in H, but when we take the sum, vector u plus vector v, we have 1/4, 1 over the 2 times the square root of 5, and we're adding v here, so that's 1/4 plus 3/4, and then for the y-coordinates, we have 1 over 2 times the square root of 5 plus 1 over 3 times the square root of 5. So for our x-coordinate, we end up with 1. And the y-coordinate here, getting that common denominator, we end up with 5/6 times the square root of 5, which certainly does not live in H. While the x-coordinate is okay, the y-coordinate is too big. So we have confirmed, therefore, H is not closed under addition. And we can do the same thing here for showing that this region, this H here, is not closed under scalar multiplication. So, okay, we have a lot going on in our vector here, but scalar multiplication is going to be easy if you simply choose one of the intercepts. So for showing that this is not closed under scalar multiplication, I'm going to let vector u here be defined as the vector -1, 0. So we can see in looking at our geometric interpretation that this vector lives in H, no problem at all. But if we multiply it by a scalar that's bigger than 1, we're going to end up with something that extends past space H. So let's look at this algebraically. Let's keep that picture there. So, again, we want to demonstrate that H, so the third condition of our subspace is that H is closed under scalar multiplication. And we are here to show that this does not hold true. So let's recall the definition real quick, that for all vectors u in H and for all scalars c, H is closed under scalar multiplication if the scalar multiple c times vector u also lives in H. So we have defined vector u as the vector in the plane with components -1, 0. Again, that's in H, no problem. If we let C, let's just let C be 2. If we let C be 2, then the scalar multiple C times vector u, so 2 times -1, 0, is equal to the vector -2, 0, which is certainly not in H. And so we have confirmed here that therefore H is not closed under scalar multiplication. So this is our first part of the solution, demonstrating algebraically that this vector, that H is not a subspace of R2 because it is not closed under addition. And this is the second half of our solution here, demonstrating that H is not a subspace of R2 because it is not closed under scalar multiplication. So if you're having trouble by simply trying to find algebraic solutions to support why this is not closed under addition or not closed under scalar multiplication, I encourage you to start with a geometric interpretation. You can then use your geometric interpretation, as we have done here, to find specific coordinates of each vector to show what you want. And one final reminder is that these two examples here are not exclusive. There's lots of other examples that work. These are just the first two that popped into my head.